In this video, we're going to look at empirical and molecular formulae. So what is an empirical formulae? Back in the days, the word empirical actually just means something determined by measurement. So originally, all these chemical formulae were determined by carrying out experiments and then working out the relative amounts of different elements present in a formula, usually by weighing the different masses of different substances that were present. And in fact, the way that we do our calculation for an empirical formula is by doing this, by comparing the masses of different atoms. The actual definition that we use at A level for empirical formula is that it is the simplest whole number ratio of elements present in the formula of a compound. And as we look at some examples, we'll see how that relates to the formulae that we generally use. So how does empirical formula relate to molecular formula? Well, for ionic compounds, they don't have a molecular formula. So ionic compounds are lattices, not molecules. They're giant structures. They've got unlimited numbers of each ion present in a single crystal. So for an ionic compound, we already write the formula as the simplest ratio of elements. So for ionic compounds, the formula that we write, like NaCl or CaCO3, is already the empirical formula of the compound. They're one and the same thing. So for covalent compounds, though, it's a little bit different. They are discrete molecules, like water and ammonia here. Now, for water and ammonia, these two examples, H2O and NH3, that is the simplest way we can represent those elements. We cannot simplify H2O any further because there's one O and there's one N in the formula of ammonia. So for those, the molecular formula, H2O, is the same as the empirical formula, H2O. That's as simple as we get. If we look at another couple of compounds though, here we've got ethene and propene, then we can see that they've definitely got different molecular formulae. So ethene is made of 2 carbons and 4 hydrogens. Propene is made of 3 carbons and 6 hydrogens. But actually the two of them have the same empirical formula. So the way that we simplify that is a ratio of 1 carbon to 2 hydrogens. Empirical formula is CH2, and in fact that's the same for all alkenes because they have this general trend CnH2n. So they all have the same empirical formula. Let's look at how we would calculate empirical formula. We're going to start using mass in grams. For this example, we've been given the mass of sodium, sulfur and oxygen that's present in a particular sample of a compound. And it's a really good idea with empirical formulae to lay it out really organised, partly so you don't write any numbers twice or get anything missing, and also so that you match the numbers to the particular elements so that when you have the ratio at the end, you don't switch them round to give like the wrong element symbols. So we're going to put in the information that we know in our table. You don't have to draw a particularly neat table if you're doing this for an exam question, just have it lined up. So we've got 3.22 grams of sodium, 2.25 grams of sulfur, 4.48 grams of oxygen. Now, the empirical formula is the ratio of atoms in a formula, or ions, depending on the type of compound. And this is mass in grams. That does not relate to the number of atoms. Moles is the thing that relates to the number of atoms. So what we're doing when we calculate empirical formula is we're calculating the moles, the ratio in moles in a compound. To do that, we need to know the relative atomic mass. So I'm going on my periodic table. Using an A-level periodic table here won't make a big difference to my empirical formulae, those little decimal places. And I'm going to do for each element mass divided by relative atomic mass. And that gives me my number of moles. So my absolute number of moles is 0.14 moles of sodium in the sample, 0.07 of sulfur, and 0.28. I then want to get that in a whole number ratio, so I don't want to be having decimal places and things like that in a formula. That's not normal, we have whole numbers. To get to whole numbers, the easiest thing is to divide each number by the smallest number there is. In the same way that in maths, for example, if we wanted to get a ratio where x was 1, we would divide x by itself to get 1. So we're taking the smallest number, 0.07, and we're dividing everything by 0.07. And what we end up with is that sodium is 2, sulfur is 1, and oxygen is 4. Don't forget at this point to actually answer the question, because what a lot of people do is get this far and go, hooray, I've done it, and move on without actually writing down Na2SO4. Okay, so that's if we got masses. Even more common than that is that we don't have absolute masses, we have percentages instead. Absolutely no difference whatsoever, because all we're imagining now is that we have a 100-gram sample and that these are masses in grams. So in 100 grams, 22 grams would be carbon, 4.6 grams would be hydrogen, and 73.4 grams would be my bromine. I'm going to do the same thing again. I'm going to look at my relative atomic masses for each element on the periodic table. I'm going to divide each element by the relative atomic mass. So I'm going to do mass divided by relative atomic mass to get moles. I get my numbers. Here's my 3 numbers. And I'm going to divide each one by the smallest number, which in this case is 0.92. And that gets me a ratio of 2 to 5 to 1. Don't forget to put the final answer, which would be C2H5Br. Okay, so far so straightforward. These you may even have done at GCSE. How does it get more challenging at A level? One thing we might have to do is work the other way around, calculating the percentage by mass of iron in a compound. So previously we were given the percentage mass, we used it to work out the formula. Now we have the formula, we're using it to work out the percentage by mass. So the percentage mass is just going to be the mass of the element. In this question we're asked to find the percentage mass of iron, divided by the molar mass, so the whole RFM, MR, whatever you want to call it, of Fe2SO43, and then to make it a percentage we multiply by 100. So my molar mass, my whole mass of Fe2SO43 is just the same way that we've done before for working out RFMs, and it works out as 399.9. The mass of iron in that is 2 lots of 55.8. Using our A-level periodic table, that gives me 111.6. Divide the mass of iron by the mass of the whole formula, times it by 100, and we get 27.9% when we round it to 3 significant figures. Okay. How about this molecular formula thing? So far we've been sticking with empirical, but we said that for ionic compounds, that's okay, empirical formula is the only formula. For covalent compounds, however, empirical formula and molecular formula might be different. So, for example, the molecule hydrogen peroxide has the molecular formula H2O2. That's the actual numbers of oxygens and hydrogens that are covalently bonded together. But the empirical formula for that would simply be OH. So, to go between the two, we have to know the mass of the whole compound. Like this example here, it says what's the molecular formula of the compound if it has an empirical formula of CH2O and a molar mass of 180. So all we need to do to answer this question is add up the mass of this empirical formula, the relative mass of CH2O, which equals 30, and then we see how many times 30 goes into 180, and it goes in 6 times. We don't finish our calculation there because we actually haven't answered the question. The empirical formula would therefore be written as C6H12O6. So what we don't do is we don't just stick a 6 in front of CH2O. That's not how we write molecular formulae. We group all the atoms together. You might recognise that as the formula of glucose. So We did say again, it's A level, sometimes it's going to get a bit harder. So how can examiners try and catch you out? The first is watch out for percentages you have to work out yourself. So for example, you're told this substance is a hydrocarbon, therefore it contains carbon and hydrogen. If it's 83.7% carbon, that means you can work out the hydrogen. The rest of the percentage must be hydrogen. So far then, this just looks like it's going to carry on and be a really easy empirical formula question. But there's another reason I chose this example. We put in our relative atomic masses like before. We work out our moles. Everything is the same. And then, because 6.975 is the smallest number, we divide both sides by 6.975 and we get a ratio of 1 to 2.33. So, do not round this number up or down, because we're only going to round our numbers if our numbers are very, very close to whole numbers. For example, 1.99 or 2.04. So we need to look out for clear, obvious fractions. The three types of fractions that you're going to get are, for example, 0.33, that is a third. To get that to a whole number, we need to times it by 3. If you have a decimal place, of course, of 0.5 or very close to 0.5, such as 0.49, that is a half. To get to a whole number, you times both of your numbers by 2. And if you have 0.66 recurring or 0.67, that is 2/3. Again, you're going to times it by 3 to get to a whole number. So if I take these two numbers and times them both by 3, then my empirical formula is actually going to be C3H7 and not CH2. So if you want some more help with your A-level chemistry calculations, I've got a full online course, which actually this video was modified from. It's called Confidence in Chemistry Calculations. And at the moment, you can get that absolutely free for 2 weeks. Let me just show you what's in the course. So there are 8 different modules which look at the essentials, equation skills, relative atomic mass, formula mass, empirical, molecular mass, percentage yield, atom economy, all these different things, titrations, loads of stuff on solutions, calculations, also Avogadro, and long answer problems. So there is some like really more challenging ones, and it comes with a full booklet of different chemistry calculations with full mark schemes and explanations as well. All of the more difficult questions that I put on there have video walkthroughs, so you don't just get a mark scheme, you actually get how to do it. Each one of these modules has like at least 6 different lessons in it, quizzes and ways to assess yourself. And actually you can access this course as part of my A-level revision memberships, which includes loads of other different topic videos and practice questions, and not just the calculations course. So the calculations course is included in the bronze, silver and gold membership. The only difference between the 3 of these is that with the silver membership, you get a full monthly assessment where you do an assessment exercise and I mark it for you, give you that examiner's perspective, give you personalized recorded feedback. And with the gold membership, there's just a few spaces left for my AQA and OCRA group chemistry lessons. Those are for year 13 because my year 12 course is full. But if you just wanted to try out the bronze membership, which is only £5 a month anyway, including the whole calculations course and 22 other different topics, along with practice questions and masterclass videos, that's actually available right now for a 2-week free trial. So you can try it, see how you get on, and if you can't even afford the £5 a month, you could sign up if you've got like a mock exam or a retake coming up. So go to my website, ckchemistry.co.uk. You'll also find loads of free revision downloads there as well. And of course, subscribe to my YouTube channel because I'm going to do at least 1 video a week and probably 2 for the next term or so.